you haven't done so yet, please pause the video and try this question first before listening on. It turns out that the best way to understand how to solve this question is to break it up into a couple of different parts. In part 1 of the question, the ball will fall 30 meters down towards the floor. In part 2, immediately after rebounding off the floor, it will rise up to a height of 20 meters. In both parts of the question, it's a good idea to list out the values that we know from kinematics. Remember, v0 is the initial velocity of the ball, v would be the final velocity, a is the acceleration, t the time, and delta x would be the displacement. Let's set part 2 aside for now and focus on part 1. Now in part 1, the ball is released from rest, so its initial velocity will equal 0 meters per second. We don't yet know the final velocity, so we'll leave that as a question mark. The acceleration will be negative 9.8 meters per second squared because the object is in free fall, and any object in free fall will have an acceleration of negative 9.8. The time that it takes to get to the floor is unknown, so we'll leave that as a question mark. Delta x, which is the displacement, is known because we know the ball fell 30 meters on its way to the floor. Just take note, however, that because the ball is moving downward, that the displacement will be negative in value. So we have to make sure that we include a negative sign in front of our displacement. Now, let's recall the following equation from kinematics. We can easily use this equation to solve for v, which again is the final velocity of the ball right before it hits the ground. Because v0, the initial velocity, is 0, we can cancel that from the equation. And then we would simply need to take the square root in order to solve for v. Recall from mathematics that when we square root a quantity, we technically get both a plus and a minus version. However, since the ball is falling downward at the end of its motion, we know that we have to use the negative sign for the velocity, so we can take away the positive value and focus exclusively on the negative value. We could then fill in the acceleration and the displacement. And when we calculate this, we should get approximately negative 24.2 meters per second. So that's going to be the velocity right before the ball hits the ground. And that's something we want to keep in mind, so let's label it on the picture. We'll come back to the importance of that velocity later on. Let's bring part 2 back into the picture. Recall that in part 2, the ball, which had just made contact with the surface of the ground, is now on its way rebounding up to the sky 20 meters. Right now we don't know the initial velocity with which it is leaving the ground. We do know, however, the final velocity because it's coming to rest once it reaches the top of its motion, so that would be 0. We could fill those values into our chart. Because this ball is simply projecting upward in a vertical direction, the acceleration again will be negative 9.8. We don't know the time that it took for the ball to get up to that highest level, but we do know the displacement. Now in this case, the displacement will be positive because overall the ball is moving upward 20 meters, so we know this is 20. Now we can reintroduce the very same equation from kinematics that we used earlier. This time the final speed is 0, so it's this side of the equation that's going to cancel out and become 0. What we'd like to do is solve for the initial velocity that the ball had just after it had made contact with the ground. So we can subtract 2ax over to the other side, and then we can square root both sides of this equation. We can then plug in the known value for a and delta x that we filled into our chart. And when we solve this, we get approximately 19.8 meters per second for the initial velocity during part 2 of the motion. So to summarize, right before the ball had hit the ground, it was moving at negative 24.2 meters per second, and then immediately after it hit the ground, it was moving at 19.8 meters per second. Notice that we can now call this the initial velocity. It would be the velocity right before the ball hit the ground, and then this would become the final velocity, which would be the velocity of the ball right after it hit the ground. And the reason that we want to frame the problem that way is because we know that while it was in contact with the ground, the time during that contact was 2 milliseconds. And so that's going to allow us to calculate the acceleration of the ball during those 2 milliseconds, because acceleration is simply final velocity minus initial velocity divided by the time interval. So let's fill in the known values for the final and initial velocities as well as the time. Notice that we converted the time to seconds by multiplying the 2.0 times 10 to the negative 3. And when you calculate this, you get approximately 22,000 meters per second squared as the acceleration of the ball, a pretty substantial acceleration. Now, of course, the question did not want the acceleration of the ball. It wanted the average force exerted on the ball. But that's easy because we know that the average force on the ball will equal the mass of the ball times its acceleration. the mass of the ball was stated in the question as 0.5 kilograms. So all we have to do is plug in the mass and the acceleration, and we have the average force acting on the ball. We've omitted the units for simplicity, but the 0.5 is kilograms and the 22,000, as mentioned, is meters per second squared. So the average net force acting on the ball becomes 11,000 newtons. And that is indeed the correct answer. Notice that the net force turned out to be a positive 11,000 newtons, just as the acceleration was a positive value. So what that means is that the net force, as well as the acceleration, point upward. As always, thanks very much for taking the time to watch this video. If you liked it, please subscribe so you can stay tuned to additional videos. You can also send in your own question to the email address listed on the screen, and the topics you can send can range from calculus to chemistry to physics and other subjects as well.